Sample and hold circuit. The sample and hold circuit samples the analog input signal and hold on its last sampled value until the input signal is sampled again. These type of circuits are used in digital interfacing and analog to digital and pulse code modulation systems. Here I am going to show you a simple and practical sample and hold circuit. Here the N channel E MOSFET is used as a switch and which is controlled by using the control voltage VC, and the capacitor C is used to store the charge, and the input signal which we are going to be sampled is applied at the drain of the N channel E MOSFET, and the control voltage is applied at the gate input of the N channel E MOSFET. Whenever the control voltage VC is positive, then immediately the N channel E MOSFET is turned on, and the time required to charge the capacitor is depends upon R0 plus RDS on into C, where R0 is the output resistance of the voltage follower A1 and RDS on is the resistance of N channel E MOSFET whenever the E MOSFET is turned on, and in this case the input voltage is appeared across the capacitor C, or the voltage across the capacitor is nothing but the applied input voltage. And coming to the second case, which is nothing but whenever the control voltage is 0, then what happened? Whenever the control voltage is 0, then the N channel E MOSFET is turned off. Then the capacitor C facing the high input impedance of the voltage follower circuit A2. Because of this, the capacitor doesn't discharge voltage across the capacitor is holding in this case. Now coming to the definitions of sample time and the hold time. The sample time period TS is defined as the time required to charge the capacitor, which is equal to the input voltage, is called as TS or sampled time period, or we may represent the sampled time period in another way. The voltage across the capacitor will be equal to the input voltage. The time is called as sampled time. Similarly, we can also express the hold time TH. The hold time is defined as the amount of the time required to hold the voltage, constant voltage across the capacitor is called as holding time. With one more thing you have to remember in this sample and hold circuit is always the frequency of the control voltage should be greater than the frequency of the input signal. The low leakage capacitors are used like Teflon to retain the stored charge. That's why what I am telling is use the low leakage capacitors like Teflon are used. And coming here, I am going to show you LF398 IC, which is used as a sample and hold circuit. It may be observed that the capacitor C is connected externally in this case, and the analog input is applied at pin number 3, and the control voltage is applied at pin number 8, which is nothing but the control voltage VC. Okay, and the capacitor, choose the value of the capacitor should be equal to 0.01 microfarad, and across the fifth pin we are going to receive the output. Once again I am telling you the basic principle behind the sample and hold circuit is sample and hold circuit samples the analog input signal and holds on its last sampled value until the input signal is sampled again. In this case, because of the voltage follower A1, whatever the input we are applied at the input of the non-inverting terminal of voltage follower, which will be obtained at the output of voltage follower and which is applied as a drain input of the N channel E MOSFET, and the N channel E MOSFET is controlled by using the control voltage VC. Whenever the control voltage VC is positive, then what happened? The analog input voltage is appeared and because of another voltage follower A2 circuit, the voltage across the capacitor is applied as an input of the A2 voltage follower and generates the output as input signal. And here I am going to show you the input and output waveforms. Here I am going to represent the input waveform Vi, and see here I am representing the input is like this, and which is nothing but the analog input voltage. Yes or no? Analog input voltage, and here I am going to draw the control voltage input, which is nothing but VC. See here I am going to take the positive, and here I am going to take the positive, and once again here I am going to take the positive. Listen carefully, always the enhanced MOSFET is depends upon the control voltage input only. Whenever the control voltage input is positive, it produces the output. Here I am getting the output as final output. Whenever it is positive, we are getting the voltage. Okay, whenever it is 0, then it hold on the previous value, and here once again it is positive, so the negative is as it is coming, and once again here it is 0, so it is holding. So once again it is positive, so we are getting the waveform is like this. So here it is holding, yes or no, until this TH, until this TH. So this is the time period TS and this is the time period TH. And one more thing you have to remember in this case is low leakage capacitors are used to retain from the stored charge. So the capacitor C may be used as a Teflon capacitor. Because of this, we can retain the signal from the stored data. The analog multipliers, the circuit which produces the output voltage, which is nothing but the product of two input voltages, is called as multipliers. And these multipliers are used in variety of applications like voltage divider, squaring of the input signal, and RMS detector, and phase detector, etc. Here I am going to show you the analog multiplier circuit. Why we are calling it as analog multiplier is if the circuit is designed to produce the output which is product of two input voltages is designed with the help of logarithmic amplifiers and anti-logarithmic amplifier, then we will be treated that circuit as analog multipliers. And once again I am recalling the output voltage of logarithmic amplifiers as well as the temperature compensated logarithmic amplifiers as well as output voltage of the anti-logarithmic amplifier as well as the temperature compensated output voltage of the logarithmic amplifier. Just I am recalling the output voltages and the temperature compensated output voltages. For the logarithmic amplifier, V0 is equal equal to eta into Vt ln of Vin divided by V reference. Similarly, temperature compensated output is equal to V naught is equal to minus K into ln of V1 divided by R into I reference, where K is equal to eta into Vt R1 plus R2 plus Rf by R1 plus RT. Similarly, the output voltage of the anti-logarithmic amplifier is V naught is equal to minus V reference into e power Vin divided by eta into Vt, and V naught is equal to I reference into Rf L inverse of minus Vin into R2 by eta into Vt R1 plus R2, which is nothing but the output voltage of the temperature compensated anti-logarithmic amplifiers. Once again, these output voltage equations I am going to be used while I am going to find out the output voltage by using the analog multipliers. So here, from the logarithmic amplifier A1 and logarithmic amplifier A2, we are going to produce the output voltages are V01 and V02. So V01 will be equal to plus K1 into ln of K2 into V1, and V02 will be equal to plus K1 into ln of K2 into V2, where V1 is the logarithmic amplifier A1 input and V2 is the logarithmic amplifier A2 input. So for equation 1 and 2, the reference equation we are considering is V0 is equal to eta into Vt ln of Vin divided by V reference, and here A3 is used as a non-inverting amplifier whose gain is unity. So output voltage V03 will be equal to plus K1 into ln of K2 into V1 plus K1 into ln of K2 into V2. So from this, log of A plus log B will be taken as log A into B. So K1 into ln of K2 square into V1 into V2, which is nothing but V03. That voltage will be applied as an input of anti-logarithmic amplifier. So finally, we are going to get the output voltage. V0 will be equal to 1 by K2 into L inverse of K1 divided by K1 into L inverse of K square V1 V2 ln of K square V1 V2. Here, if you observe this, K2 will be equal to 1 by V reference, where V reference will be taken as I reference into R. Similarly, here also we are going to take K2 will be taken as 1 divided by V reference. Okay, so what we are going to get is finally V0 is equal to 1 by K2 into ln inverse, and ln is cancelled and K1 is cancelled, K2 square into V1 into V2, K2 square K2 cancel, so we will get it as K2 into V1 into V2, which is nothing but output voltage V0. Finally, the output voltage will be equal to the product of two input voltages, which is nothing but V1 and V2, where K2 is nothing but a constant. So by using logarithmic amplifiers as well as anti-logarithmic amplifiers, we can produce the output voltage which is nothing but the product of two input voltages. This is called as analog multipliers. Multiplier integrated circuit. Monolithic integration lowered the cost of multiplier integrated circuit. Because of this, the multiplier integrated circuits are not only used as a multiplier, they can also be used as a simple and direct solutions of complex signal processing problems. and multiplier integrated circuits are used in several applications. They can be used as a voltage divider, they can be used as a frequency multiplier, and they also used as an RMS detector, and they also be used as a phase detector, etc. Now we are going to see all those applications by using the multiplier integrated circuit. Here I am going to represent the basic multiplier circuit. The basic multiplier circuit is a active circuit which consists of two supplies, which are nothing but dual supply is required for the integrated circuits. Generally we are applying plus or minus 15 volts, and which consists of two input terminals X and Y. At the two input terminals we are going to be applied the two input voltages like V1 and V2. And at the terminal Z we are going to receive the output, which is nothing but the basic multiplier circuit. Once again I am repeating the definition. The basic multiplier circuit is an active circuit which produces an output voltage which is nothing but the product of two input voltages which we are applied at the two input terminals of the multiplier. Generally we will be treated that V0 is equal to K into V1 into V2, where K is nothing but the constant of proportionality. Here we will be treated it as K is equal to 1 by V reference. So V0 is equal to V1 V2 divided by V reference. Generally we will be set V reference will be equal to 10 volts. So the output voltage of the active multiplier circuit will be equal to V1 into V2 divided by 10. And one more thing you have to remember in this case is until the V1 and V2 values are less than V reference value, then we will not get any saturated output. We will get the exact output for the whatever the input we are applied at the input terminal. Once the inputs are crossing the V reference voltages, then we will get the saturated output voltages. So this is very important in case of active multipliers. So V0 is equal to V1 into V2 divided by 10. Depending upon the usage of the basic multipliers, we are going to restrict the polarities of the multiplier. So whenever the polarities of the multiplier is restricted, depending upon the input polarity restrictions, the operation of the multiplier ICs are divided into first quadrant multiplier, second quadrant multiplier, and fourth quadrant multiplier. In the first quadrant multiplier, both the input polarities of polarities are positive polarities, whereas in case of second quadrant multiplier, one input polarity should be positive and the other input polarity may be swings between positive and negative. Coming to the fourth quadrant multiplier, in this case both the input polarities are swings to negative polarities as well as positive polarities. So whenever we are going to explain the multiplier circuit, depending upon the input polarity restriction, we are going to be used any one of these multiplier types. Coming to the application of multiplier integrated circuits. First application is voltage divider using multiplier. The circuit in which output voltage is division of two input signals is called as voltage divider circuit, and by using the multiplier, here I am going to represent the voltage divider circuit. Coming to the A1 op amp. The current drawn at the input terminals of an op amp is 0, or the input current will be equal to the output current. And see this one, the node A is connected to ground. According to the virtual ground concept, the node B is also connected to ground. And now calculate IN. Okay, so IN is equal to VN minus VB divided by R, where VA is equal to 0. So according to the virtual ground concept, VB is also equal to 0. So IN will be taken as VN divided by R. And next, what I told you is the input current drawn at the input terminals of an op amp is 0, or the input current will be equal to output current. Here I am going to calculate the current IZ. IZ will be equal to VB minus VZ divided by R, where VB is equal to 0. So we will get it as IZ is equal to minus VZ divided by R, where VZ is nothing but the output voltage of the multiplier. We all know that the output voltage of the multiplier is nothing but the constant K into product of two input voltages which we are applied at the input terminals of the multiplier. So here I am going to treat VZ is equal to K into V0 into VT. Okay, so substitute in this equation. So we will get it as VZ is K into V0 into V2 divided by R. So I told you that the input current will be equal to output current. Take it as equation number 1 and take it as equation number 2. So 1 is equal to 2. So we will get it as Vn divided by R will be equal to minus K into V0 into V2 divided by R. R cancel. From this V0 is equal to Vin divided by minus V2 into K. So which is nothing but output voltage is nothing but the division of two input voltages, which is voltage divider. Here we are using the multiplier circuit for the designing of voltage divider. So we will be treated it as voltage divider using multiplier. Squaring circuit using multiplier. The squaring circuit using multiplier produces the output voltage which is nothing but the square of the input voltage. In this case, both the input terminals X and Y are connected together. So the input voltage V1 is applied to both the input terminals. So we will get it as V0 is equal to K into V1 into V2. So from this we will get K into V1 square. We all know that K is equal to 1 by V reference. Okay, so from this expression what we can conclude is the output voltage is equal to square of the input voltage. That's why we are treating it as a squaring circuit using multiplier. Square root circuit using multiplier. Similar to the squaring circuit using multiplier, we can also design the square root circuit using multiplier. In this case, the multiplier is configured as a squaring circuit and which will be connected in the feedback path. And the op amp A1 used as a inverting op amp, and the gain of the op amp A1 is treated as A, and the input voltage applied between the inverting and the non-inverting terminals will be taken as Vin. From this we can write the output voltage of op amp A1 will be written as V0 will be equal to minus A into Vin. From this Vin will be equal to minus of V naught divided by A. Take it as equation number 1. If you observe this circuit, here V in is composed of two components. One is because of Vz and the other one is because of V in. So V in will be rewrite as V in will be equal to, first I am considering it is composed because of Vz. So Vz into R2 divided by R1 plus R2 and then plus Vn into R1 divided by R1 plus R2. Take it as equation number 2. So Vn is generated because of Vn and Vz, and here the Vz output is occurred because of the squaring multiplier circuit. So Vz will be equal to K into V naught square. Here the output voltage is applied as an input of multiplier circuit. Here the multiplier is used as a squaring circuit, so both the inputs are connected together. That's why here I am writing Vz is equal to K into V naught square. Take it as equation number 3. Substitute into, we will get it as Vin is equal to K into V naught square R2 divided by R1 plus R2 plus Vn into R1 divided by R1 plus R2, and we all know that V1 is equal to minus of V naught by Va, and substitute 1 in this equation, then you will get it as minus V naught by A will be equal to K into V naught square into R2 divided by R1 plus R2 plus Vn into R1 divided by R1 plus R2. So from this we can rewrite it as take this as that side and this term as take this side. So you will get it as K into V naught square R2 divided by R1 plus R2 is equal to Vn into R1 divided by R1 plus R2 plus V naught divided by A. In this, take common as Vn into R1 by R1 plus R2, then you will rewrite it as Vn into R1 divided by R1 plus R2 taken as common 1 plus V naught by A into Vn into R1 into R1 plus R2. Okay, we all know that the gain of the op amp is very high. Here it will be in the denominator position, so the total term will be very much less than 1, so we will be neglect that term. Finally we will get the equation as K into V naught square R2 divided by R1 plus R2 will be equal to Vn into R1 divided by R1 plus R2. Okay, here we are having minus. Okay, so here also we will get it as minus. From this R1 plus R2 is cancelled. From this we can write it as V naught square is equal to minus Vn into R1 divided by R2. So finally we can rewrite it as V naught is equal to square root of minus Vn into R1 divided by K into R2. So if you observe the output expression, V naught will be equal to square root of input voltage. And listen, an important point in this case is always taken Vn as negative value, otherwise the circuit is latched up and it will break the feedback path. Why? Because if you have taken Vn as negative, because of the cutting configuration we will get the output as a positive voltage. Why? Because we will getting 180 degrees phase shift with respect to the input, then it will be act as a switch. So to avoid this we are going to be used a diode. D is connected in series to the output voltage. Frequency doubler using multiplier. Here we are going to consider the two input signals which are having same frequencies but possibly they are having different amplitudes and phase angle gives the signal of double frequency, which is nothing but frequency doubler. Considering V1 is equal to V1m into sine omega t. Take it as equation number 1, and V2 will be taken as V2m into sine omega t plus theta. Take it as equation number 2. Okay, so the output voltage V0 will be equal to K into V1 into V2. So what we are getting is K into V1m into sine omega t into V2m into sine of omega t plus theta. So we all know that sine A plus B is equal to sine A cos B plus cos A sine B. So expand that equation. V1m into sine omega t, V2m into sine of A cos B plus cos A sine B. Okay, so from this K into V1m into V2m sine square omega t into cos theta plus cos omega t into sine omega t into sine theta. Okay, from this we can get the output voltage will be equal to double the input frequency. How can we get it? As sine square theta is equal to 1 minus cos 2 theta divided by 2, and cos theta sine theta will be equal to sine 2 theta divided by 2. By using those two trigonometric expressions, we can easily solve this equation. So we will rewrite it as K into V1m into V2m, and sine square theta is equal to 1 minus cos 2 theta divided by 2 into cos theta plus sine 2 omega t divided by 2 into sine theta. Okay na? So from this what we can write is V0 is equal to K into V1m into V2m into cos divided by 2 into cos theta minus cos 2 omega t into cos theta, and then plus sine 2 omega t into sine theta. And we all know that cos A cos B plus sin A sin B is equal to cos A minus B. By using that expression, V0 is equal to K into V1m into V2m divided by 2 into cos theta. If you have taken minus as common, then cos A cos B minus sin A sin B, which is nothing but cos A plus B. So cos of 2 omega t plus theta. Okay, so from this expression what we can write is V0 is equal to K into V1m into V2m into cos theta divided by 2 minus K into V1m into V2m divided by 2 into cos of 2 omega t plus theta. If you observe the final expression, what we can conclude is the output voltage consists of the DC term along with it consists of an AC term which is varying with respect to the time t. Okay, and if you observe this expression here, the frequency is double that of input frequency. Okay, so if you have taken the multiplier is like this, x, y, here you apply the input as V1 and you are apply the input as V2, and there you are going to collect the output. Frequency doubler using squaring multiplier circuit. Here both the inputs are connected together and the same input voltage we are applying to the both the input terminals. So here I am going to consider Vin is equal to Vm into sin omega t. In the previous case, we consider both the inputs are having same frequencies but they are having different amplitude and phase angles. In this case, all are same. So, the output voltage V0, which is nothing but first I am going to calculate the output voltage of the squaring multiplier circuit. Vz is equal to k into Vin square, which is nothing but k into Vm square into sine square omega t. Sine square theta is equal to 1 minus cos 2 theta divided by 2. So k into Vm square into 1 minus cos 2 theta divided by 2. From this we can rewrite it as k into Vm square by 2 minus k into Vm square into cos of 2 omega divided by 2. Okay, from this what we can conclude is if you are passing the output of multiplier through the capacitor blocks DC and allows only AC signals. So the output voltage V0 will be equal to minus of k into Vm square into cos of 2 omega t divided by 2. From this output expression, what we can conclude is the output voltage is nothing but the doubling of frequency. Another application of the multiplier integrated circuit is phase angle detection using multiplier. Here at the output we are going to connect the DC voltmeter considering the output voltage expression from the frequency doubler using multiplier. V0 is equal to k into V1m V2m into cos theta by 2 minus k into V1m V2m cos 2 omega t minus theta by 2. That is V1 will be applied as V1m into sin omega t and V2 will be applied as V2m into sin omega t plus theta, which is nothing but which consists of both the input signal frequencies are same but they are having different amplitudes and phase angle. If you apply both the inputs at the inputs of multiplier, we will get the output voltage as like this, and the DC voltmeter responds to the DC term only. It will not be respond to the AC term, so it accepts the DC term only. Finally we are getting the output voltage V0 is equal to k into V1m into V2m into cos theta divided by 2 and choose the phase angle. Theta is equal to 0 degrees, theta is equal to 45 degrees and theta is equal to 90 degrees. Then we can easily calibrate the phase angle between the two input signals by using a DC voltmeter. So first I am choosing theta is equal to 0 degrees. Then output voltage V0 is equal to k into V1m into V2m divided by 2. Then theta is equal to 90 degrees. So V0 is equal to 0 and theta is equal to 45 degrees. Then V0 is equal to k into V1m into V2m divided by 2 into root 2. Okay, so by using the DC voltmeter we are calibrating the phase difference between the two input signals which we are applied at the two input terminals of the multiplier. So with this circuit we are going to calculate the phase angle between the two input signals. That's why we are going to treat the circuit as phase angle detection using multiplier. Another application of the multiplier integrated circuit is RMS detector. Here it consists of three circuits. First one is squaring circuit, and the second one is integrator. Last but not the least is square root circuit. By using all these three circuits, we can calculate the output voltage is root means square value of the input voltage. We are applying the input at the squaring circuit. We produce the output as the square of input signal, and with the help of integrator, we are going to integrate the output of the squaring circuit. We generated the output at the output of integrator, and the output of the integrator is square root. By using this square root circuit, finally we are going to get the output voltage as root means square value of the input signal. With the help of this circuit, we can calculate the RMS value of the input signal. Last application of the multiplier integrated circuit is rectifier circuit using multiplier. By using this circuit, we can generate the full wave rectifier. The op-amp A1 is used as a non-inverting comparator, and the output of the op-amp A1 is Vk, which is nothing but a square wave output. That means which produces the output as a plus or minus Vsat depending upon the input voltage which we are applied at the non-inverting terminal of an op-amp. If you compare these two inputs, if Vin is greater than this voltage, then we will get the output as plus Vsat, and if Vin is less than this output, then we will get it as minus Vsat. And here we are using the 4-quadrant multiplier. Always the output of the multiplier is a positive value, and the output of the comparator A1 is a square wave which is applied as one input of the multiplier, and the other input of the multiplier is directly applied from the input signal, and this is the 4-quadrant multiplier. Always the output of the multiplier is a positive value. That's why we are calling it as a absolute value circuit. By showing the input and output waveforms, I am going to explain how it is full wave rectifier circuit. Here I am going to take the input signal T, and here I am taking it as input signal, and here I am considering it as Vk, which is nothing but the output of non-inverting comparator. So whenever Vin is greater than, here the reference is 0. If Vin is greater than 0, we will get plus Vsat. If it is less than, then we will get minus Vsat. Again we will get it as plus Vsat. And here I am going to write the multiplier output Vz. Okay, so if we are multiplying positive value with positive value, then obviously we will get a positive value, and negative value with negative value, then we will get a positive value. Again positive with positive, we will get the output as a positive value. That's why I told you that the multiplier used in this case is a 4-quadrant multiplier. In case of 4-quadrant multiplier, both the input polarities are swings to positive polarities, or both the input polarities are swings to negative polarities. While you are going to multiply the input voltages, obviously we are going to get the output voltage as a positive polarity. Like this, we are going to get the output voltage of the multiplier is always a positive value. That's why we are calling it as a absolute value circuit. By using this circuit, we generated the full wave rectifier.